So we're going to talk about strong acids and bases on this first slide. We'll talk about weak on the next. And then on the last slide, I'm going to use the Alberta 2030 data booklet to connect weak and strong and where they are in your data booklet and how you can make predictions. So strong species break up 100%. So if you have 1 mole per liter of hydrochloric acid, which is strong, that whole 1 mole per liter will turn into hydronium. And we'll see that visually in an equation in a second. Okay? Because of that 100% conversion, we can actually get hydronium concentrations. Okay? So an example of a strong acid is perchloric acid, HClO4. The very top one in the Alberta data booklet that we'll see in 2 slides from now. If I write the modified Arrhenius equation, it's going to react with water. So HClO4. It's going to make hydronium ions. The H comes off the ClO4 and the charge goes from 0, which I didn't write. We don't write in charges of 0, but you have to realize it. You lose an H+, it drops to minus. In our modified Arrhenius equations, we always have one of all the species. So every one of those will turn into one of those. Okay. And strong means this happens 100%. None of our original reactant is going to stay together. So if we have 1.0 moles per liter of perchloric acid at the beginning, 100% of it will turn into hydronium. So at the end, would have 1 mole of that, which would let you figure out the pH of the solution. Okay? The pH is equal to the negative log of hydronium, okay, which is going to be the same as the original acid before it broke up 100%. You take the negative log of 1, and you get a pH of 0. Any original strong acid above a concentration of 1 will give us a negative pH. Okay. Now we can do the same type of things with basis or realize the same theory. Now we don't have any modified with strong basis. So I did a modified equation with water, strong basis just dissociate. So if you have sodium hydroxide, you put that into water, or it's in water, it's going to 100% dissociate. No water is needed because the dissociation by itself gives us the hydroxide. Okay. If I have 0.10 moles per liter, okay, 100% is going to dissociate, and we're going to end up with 0.10 moles per liter. Okay. So we could figure out the pH again. Okay. But it's going to take a couple steps now. When you have hydroxide, you have to get the power of hydroxide first. Okay. If you take the negative log of that, that's not pH. We have to take the negative log of hydroxide, and we're going to get 1.00. Okay. There are 2 significant figures in my concentration, so that's why I'm writing 2 decimals. Okay. It's an outcome of Chemistry 20 that students know how to do proper sig figs with power of calculations. Okay. So the pH, I'm not going to show my work. The pH and pOH sum to 14. So the pH is 13. Okay, the 1 and the 3 aren't our sig figs. It's just the 2 decimal places. Okay, we can't do any of this with weak species because they don't break up 100%. Now, the other sort of strong base category, calcium hydroxide, can produce hydroxide in solution. Now, here you have to watch out. Every amount of calcium hydroxide gives double the hydroxide. So if we had 0.0001 moles per liter of calcium hydroxide, we're going to get a doubling. Now, I picked very low numbers this reason on purpose. I'm going to star this. Calcium hydroxide is not very soluble. So you can't put a very high concentration into water because it'll just precipitate on you. Okay? But group 1 cations with hydroxide are very soluble. So you can have really high concentrations of the group 1s, not the group 2s. You're not being tested on this solubility, so you don't have to worry about that precipitation. You would assume whatever amount I gave you was actually soluble, and you'd do the doubling. So that's strong. Okay. I'm saying it over and over again, but I'm really trying to emphasize this 100%. It's the only time in Chem 20 that you can take the acid concentration and tell me the pH. Okay. Our weak species only transfer a little bit of their H's to water. Now, when we write weak, we always do modified. Okay? There'll be no just associations here. Okay. So hydrofluoric acid is a weak acid. Acids transfer the H to water. Okay. Arrhenius theory said the H comes off. Modified Arrhenius, it actually connects to a water. So our water is where we get our acidic species. The HF turns into F minus. Okay, the charge is always dropping 1. Okay, so we don't write in that hydrofluoric acid has no charge. We have to realize that when we take away an H plus to drop at 1. Okay, this is a weak species. This will be less than 100%. If we have 1.0 moles per liter of HF, of original reactant made up, we're not going to get 1 mole per liter of hydronium. Okay? Only a small fraction of the H's will come off. So all we know is we're going to get less than 1 mole per liter. Okay? Within Chem 20, we're not going to go past that. Now, if you take the negative log of 1.0, you get a pH equal to 0. Okay? But we're not going to get a pH that low. We're going to get a pH somewhere above 0, okay, depending on how many H's transfer. Okay? And it's chemistry 30 that you learn how to do the math with weaks. Okay? Chem 20, you know how to do the math with Strong's because it's 100%. So doing these type of calculations are coming. You're a year away from it. Okay. So that was a weak acid, weak basis, exact same type of theory. So if we have a 0.1 mole per liter solution of ammonia, ammonia doesn't contain any OH. It is a weak base. We'll see on our next slide, I'll put up the data table, which is where you'll get the evidence that this is weak. I'm going to write the same type of statements underneath, concentration-wise with the acids. So if we start with 0.1 moles per liter, okay, we're not going to get 0.1 moles per liter of our ammonium. We don't know exactly how much, but we know it will not be 0.1. It'll be something less than 0.1. And again, this is the type of question that you would answer in chemistry 30. What is the pH, okay, or the pOH? How much ammonium or hydroxide would be made? So let's take a look at page 8 and 9 of your data table to help guide you in figuring out whether something is weak or strong. So I've taken your table and put some coding in it. I've put red boxes around your strong species. So we'll start at the top. Okay. The acid table has all your strongs at the top above a gray line, okay, above the hydronium ion. Okay. Okay. We're not using these K values this year, but when something is strong, it makes all products, and those K values are ratios of products over reactants. When you try to do products over reactants, when you only make products, you get an infinitely big number. It approaches infinity. So that's why you don't see any numbers in the K column. They're all a tie for strong. So your strong acids are here. As you go down, and there's a long way to go down, they get weaker and weaker and weaker. The weakest acid is at the bottom of the acid column. So you've got a bunch of ties for strong acids in the red box. Then you've got a purple box that's labeled weak, and they're in order. Okay. So the best of the weaks is oxalic acid. It's still not 100%. It's less than 100, but it's the best of the weaks. And you go all the way down. So hydrogen phosphate ion is an acid, but it's maybe 1 in a million transfer. Okay. Bases are the opposite. The only strong base are those dissociations to hydroxide. So the strong base is here, and as you go up, they get weaker. So there's a lot of looking things up in your table to figure out its strength. Okay, we'll build upon this in the next lesson. Polyprotic species is next.